presumably exact same rules, except you can capture any dice from a third player as well, or reroll any dice from a third player, or use your card on the third player.
Wait, right, I'm just curious then, would you do like a different ordering maybe? Would you like do like baton ordering?
How do you do baton ordering?
So basically, you do 1, 2, 3, 4, and then 4, 3, 2, 1.
Oh, that's kind of cool. Maybe. I feel like I'd have to play that a few times to kind of figure out what would work best.
So when you have, because in that case, if you have multiple players going first, it starts to become a larger and larger advantage.
Mm-hmm. Yeah, as the games progress over time,
Or I suppose going first, going last.
Actually,
or is there any advantage? I'd actually be curious if there's any significant advantage now that I think about it.
The way I get around first turn advantage in this game is the black player gets to reroll one of their dice at the beginning of the game, and then white goes first.
I see what you're saying.
So that way, like if you're the black player and you just roll like an awful hand, white can't just immediately capture your d20 and end the game for you.
I suppose the hard thing would be like everyone just like picked one player.
Just bully them.
Yeah.
Yeah.
That would be the difficult thing to balance.
I think the win condition would have to change from the player that made the last capture to the player that made the most captures.
That would also help.
People, questions about anything? Me?
What should we study for exam 3? There's been for exam 1, there's been like a lot of stuff that we've covered. I feel a little bit lost trying to begin.
I don't know if anything that is excluded. Of course, there will be a list of the material out there. Right now, I just tell you up to some points, which is probably all the way until what we'll discover today, Thursday, which is approximated nearest neighbor. Maybe approximated nearest neighbor will not be included. But definitely everything up to and including what we discovered so far. So definitely duality for everything up to duality for sure, maybe included approximate nearest neighbor. As far as material that I showed you, there are proofs that I showed in class that you studied enough that I want you to be able to reconstruct the proof, and there are proofs that I thought that were more technical, and maybe it's less important as long as you understand what the proof is trying to say. Usually I don't show a lot of the proofs of the other part, because if there is nothing to study with it, then maybe we pass on it. But a example of it was that a balanced quad tree has only 36 many nodes more than what the unbalanced of the same tree has. So that was a proof that I said, yeah, it comes from very good reasons, but it was a bit technical, also the way it presented. But what other things would you not want to be included?
Line sweep.
Hmm?
Line sweep.
Too basic. Line sweep will be there in many ways, because I don't think about line sweep as a single algorithm. It's a big train platform that you can stack on it, a lot of different applications. And like we saw last time, that if I want to compute union of bunch of objects, union of segments, union of lines, union of everything, I can do it by partitioning them to pairs. It was in the case of union of, to compute lower envelope of lines, but the same technique would work on many things. I want to compute the union of all these balls. 1, 2, 3, 4, 5, 6 balls. I want to compute their union, meaning I want to know what is the boundary of this shape, and the boundary is something that looks like the boundary just meet everything on between, and the boundary might even miss some of the balls inside that are well buried. The algorithm that you know to compute the union of balls, first you know why it's important to compute the union of balls. That's for robotics. But compute the union of balls, what you'll do is take the balls, take balls 1 and 2, so only balls 1 and 2, and compute them in the intersection point using line sweep. And same goes for balls 3 and 4, and compute the union of 3 and 4 separately, and then you compute the union of these two pairs. And so such a tree of line sweeps is recursive calls to line sweep is pretty general too. So, so I hear you, but unfortunately that I'm not going to exclude lines. But what other things would you not? It's a question to all of you. What other things would you really hated and not want me to include?
Have you decided, is it an open book or closed book, or is it in the classroom?
I think that it will be closed book because of, change the path, because I'm still playing with silly ideas like it will be an open book, but you're only allowed really large letter and only one page of it, so you have just limited in the material, or only allowed to take copies of slides. It's maybe less of a thing. But at the moment, assume that there is no cheat sheet. That's a meaning. Like, because you see what I'm saying? Because like earlier years, I knew that people can get to other resources, but you either copy the other resources and then you have the answer in your cheat sheet. You can even do it very well, but for many resources, many questions, bring the solution to everything that you found on chat.com. That bring it up, and that's your cheat sheet. And that by itself start to be annoying, but I could have survived with this because I can always come up with more questions that doesn't fit it. But with cheat sheet now, I start to lose the race. You can think about other variants A and but even if I didn't solve it directly, ChatGPT will solve it maybe correctly for you, so you can guesstimate what I might ask. So again, and ahead of time and type it, and B, that if two of you can have the material from ChatGPT, but it will look completely different. So it will not indicate directly that it's not original. So because of it, I would much rather say that you study much more from open book exams, but not in the presence of ChatGPT. Yeah.
Do we need to know R trees, KD trees, and quad trees, or can we know just quad trees for the exam?
Everything that we said about all three.
Okay.
They're important. We spend a lot of time on all three. So everything we said about all. If you want to exclude something from it, it's a trick of the log n to find a key. I'll think if I want to include it. It was slightly tricky. And it doesn't appear in your textbooks. How do I do the search in log n instead of just in log age instead, just order age? Other thing, yeah.
Will you make any previous exams from previous terms available for us to study from?
Happily. Yes. I can definitely show you that. Keep in mind the material might be slightly different, and that it was open book exam, 4 pages. You see it, but beside it, sure. I'll share with you, and the other thing you need to know, usually, I told you, I'm giving you n questions, you have to answer usually n minus 2. Give you 5 questions, I ask to answer 4, 3, maybe it's 6 and 4, something like this. And I don't want time pressure to play too much of a role. Should be some frame, but it's better if you don't plan something that happens immediately at 6:15. If you want to take an extension, that will have the option. And if you're a DRC student, and usually you receive more time, then you can take it at the DRC office, but you can also stay during the exam here with me, and we'll just continue later. And being here with the class has the option of that I can communicate and answer questions and clarification better than if you are stuck in the DRC office, and it's very hard to tell you, student John Smith just had a great question that I needed to change to add explanation to the question, and how do I communicate it to somebody at the DRC. So again, if you're a DRC and usually you have more time, then you have the option to take it here in the classroom or simultaneously in my office at the same time, the time of the exam, and continue until we are done. So if I had the exam, say, would take an hour and a half, then the DRC student will stay 3 hours. And yeah. Okay. Material for today does not appear in the 4-mark textbook. You can find it in Sariel's pretty advanced, fantastic book on geometric approximation. You can find it on Mount. There is a link of Mount lecture notes, Dave Mount, from University of Maryland. Both of them also contributed a lot to by now it's a long sequence of algorithms to do approximate nearest neighbor. And it's my decision here to say that it's nice when we are taking a problem that naively, like line sweep, solve something in n square, and from n square time we are moving it to n log n. Yeah, there is satisfactory here. Sometimes it's practical, but it's not nearly as practical or not nearly as important as it was 30 years ago when computers were much slower. So if we want to have more contributions that are relevant for today's computers, not to 1980s computers, then line sweep by itself is not you will not get excited from line sweep because it moves you from n squared to n. But what happens with finding nearest neighbors? Finding nearest neighbor in the 2D plane, we can find them exactly by building Voronoi diagram or Delanoy triangulation. And remember, when I'm asking about Voronoi diagram, I'm asking about actually two things. Voronoi diagram is a partition of the plane into the cell, into the sides, and then for a query point, I want to find who is the nearest point to the query point. So I need also a data structure that will be tailored, this one we did not exactly cover, that can tell me who is a cell that contains my query point. But that's my application of the Voronoi diagram, just to answer nearest neighbor queries. So Voronoi diagram in 2D, as we mentioned, Voronoi diagram of S is P1, Pn. And I'm talking about Voronoi diagram of Euclidean distance Voronoi diagram. Euclidean, d of a b equals the sum of a dot xi minus b dot xi square. I goes for 1 to b and all of it squared. But, so you look at the x, then y, then z in each coordinates. Look at the gap of the coordinate and coordinate I between ai and bi. Look at the square of all these numbers, sum them up, and then take square root. It's just Pythagoras with a lot of numbers. But I just mean that in 2D it would be a dot x minus b dot x square plus a dot y minus b dot y square. All of it is square root, same thing. So that's a L2 distance. The Euclidean or the L2, no. And we are very happy with the exact Voronoi diagram that we computed, and it works in 2D. Now, Voronoi diagram of S in 3D, what's the complexity? Help?
Plus AZ minus BZ equals, oh, complexity.
Hmm.
Is it n squared log n?
Theta of n squared, the log n, right?
Because I thought the time it took to construct a two-dimensional is n
No,
log n.
just the complexity, how many vertices, edges, parts. It's not about the running time, it's independent of the algorithm. If I need to end up with a geometric structure that has the cells, the faces, the edges, how many geometric features can I have? And how can we prove that that's a complexity?
this might not be right. But we know a Voronoi diagram in 3 dimensions, each edge is going to connect 3 different points, or is going to be equidistant from 3 different points. So there, I want to say there's n choose 3 possible points, which is on, or possible edges, which is on the order of n squared.
N choose 3 is order of n 3.
I think binomials are n squared.
Number 1.
Oh, okay.
So yeah, how do we know that it's omega of n squared? That it's no less than n squared.
Can you project it into 2D and then project it back? Is that? It's a parabola, right?
It's related to parabolas.
So you roll a ball, you demonstrated, you roll a ball.
Repeat, please. Just
Yes.
let everybody hear.
So your equidistance between the tangent and the other tangent. And you roll a ball, it looks like a parabola, so it's
We saw in class example with a basketball and another ball of 2 different radii, and we said that we can have a set of S, which was a set of points. We think about S as the union of S prime, union of S double prime. These are 2 sets of points. One set of points was on the perimeter of a clock, like our alarm clock that is standing over here. One other set of points were on a line where I allocated my points along this line, and then I had to prove to you that for every pair of points, one from here and one from here, I can find a ball that will touch only these 2 points and will be further away than any other point. That is, the center of this ball will say the nearest neighbor is 1 point here that I tell it to pick, 1 point from here that I tell it to pick, and my distance from the center of the ball to every other point is larger than this number. And that's how I prove that there are n squared many bisectors of this Voronoi diagram. Good. Repeat the video part that showed it because I really needed to lie on the 3D structure. Yeah. And convince yourself that it's also order of n squared, that it's the complexity of the Voronoi diagram or in 3D. Can I create Voronoi diagram with quadratic complexity in the plane? Yes, but not just points and not under Euclidean. We had an example that yes, you can stay in the plane, but then you need to play with a weighted Voronoi diagram. Okay. So is it feasible to build the exact Voronoi diagram in 3D? In 3D, you can build the Voronoi diagram explicitly. Doable. It's the common claim is that the actual complexity on average is about n square root n. So it's not too bad for average set of points that's expected. Complexity, so you can still get away with. Okay, but what happens when d equal something else, anything when d start to be larger than 4? So this that is larger than 4, then the complexity is about order of n over d half, now in a ceiling. So we cannot build Voronoi diagram in higher dimensions. Well, we can, but they are practical only for very small inputs. We can use various hacks. As I mentioned, quad tree, KD tree. You can use them to find nearest neighbor. It doesn't come with guaranteeing on the time, but on average, it becomes quite practical. But no guarantees about the worst case. And for some inputs, using KD tree or quad tree will be you'll be horrendous about the running time. What can you do in higher dimension is what we are going into now, and it's much newer material. Yeah, let's just summarizing it. Voronoi diagram in different dimensions for points in high D. Need a data structure to find the nearest neighbor query. Given a query point, find the point, the site of S closest to Q. In 2 dimensions, we just have the simple Voronoi diagram, compute the Voronoi diagram, build the trapezoidal map of the cell of the Voronoi diagram. It's something that we will use formally later when we get to robotics, but what is trapezoidal cell? So I run a set of segments, and here are my set of segments that I created. So you see 3 cells that I created, just to give you a very, very quick promo about what is trapezoidal map. So you see 3 polygons here. I can triangulate them. If I want to break them into smaller pieces, so point location will work better, not to have large complexity shapes. If I want to do any type of simulation, break them into triangles is one option. Simpler option is to break them into trapezoids. How do I break them into trapezoids? I'm saying I see a vertex here. Let's shoot vertical way. Vertical. So all the segments that I'm going to create will be always vertical. And I'm going to shoot this way from one vertex until I hit one of the edges. And from this guy, I try from this vertex, I shoot a vertical way down until I hit one of the segments, and then I stop. And I possibly also from this vertex shoot one up. And I'll have another one right here, shooting it from here, shooting this one from here. So in both cases, I shoot a vertical way up and vertical way down, and I stop the moment that I meet the next segment. So if I have a bunch of more cells coming up over here, this way is blocked by the floor of by the floor beneath me, or by the roof just above me. So once again, from any vertex, hit a vertical way up, vertical way down, until you find one of the edges. And I do it from any vertex. And my question for you, since we are starting preparation to the midterm, even though we didn't talk about vertical decomposition yet, let's play with this example for a moment. What are the shapes that I'm getting? What
Parallelogram?
every cell that I'm getting, warm but not exactly.
Is it one line vertical and the other line is
All the lines that
perpendicular?
all the segments that I created in red, they are all vertical.
Oh, they're all vertical, but how do you determine the next starting point on the next?
I always start from a vertex. I start from a vertex, and from the vertex I shoot a vertical way down
Okay.
until I hit any object of the original shape.
Mm-hmm.
And similarly, I'll shoot one also up until I hit the
Oh, I see.
shape.
Okay, because you didn't stop. Did you start with the vertex there?
Which one?
When you started that one on the left, upper left, the first line to the
Left, right?
first line on the left that you started. Yeah.
Here, this vertex.
Oh, that's a vertex? Oh, okay,
Yeah,
I'm sorry.
that's the intersection of
Okay,
these two.
didn't see, okay, thanks.
Okay, yeah.
So looking at this, we know every line that we create is vertical. We also know that every region we create is going to be bounded by an upper and a lower section from our segments. And if each of these lines are perfectly vertical, the other two lines are going to be parallel, so it has to be parallelogram. Because
It could be accidentally that it's parallelogram. It accidentally will be parallelogram, but it's not the general case.
why is it not guaranteed?
Yeah, you wanted to answer? Okay.
I was gonna say the trapezoidal.
Trapezoidal,
Yeah.
because this and this, the red ones are parallel to each other. The other edges do whatever they want. So it's trapezoidal map. Two edges are parallel to each other, the other one do whatever they want. What?
Do you have some kind of detection for like an upper and lower bounds? Like you see that one usually goes like super far down.
I never penetrate into, it's very soft way that I'm doing. But the moment that I hit any of the other walls, any data, any segment of the map, I stopped, that indicates stopping point.
You know, if you wouldn't have something underneath it to hit, do you have like a lower?
Then I put everything in a box. And that's essentially true for all our algorithms. They always live inside a box. Okay, so how many such trapezoids did I create, or how many walls did I create? The number of vertices times 4.
Yeah.
How many cells do I have? We might want to use Euler for it. The number of cells is roughly the number of vertices, which is linear. I partition the planes into trapezoids. Hence, it's called trapezoidal decomposition. And it's easy in the sense that if you have a point that landed at some point, then you know on this face who is a segment above me, below me. If it's a cell, it comes from a side. If I gave you just the original segments, how describe an algorithm that compute trapezoidal decomposition? That's a question, slowly. Everybody. So I give you a set of segments, what you see as a black segment, and I want you as a return to have a DCL of the trapezoidal map. You know, DCL implies faces. In this case, face must be a trapezoid. And of course, for each trapezoid, who are the guys, who are the neighbors, everything that you know in DCL. So how long will you take, and which algorithm would you use? That's a very legit midterm question.
What's that divide and conquer? Just like the.
You could, you don't need to. It's a bit. Just trying to identify people that didn't speak. Yeah.
So I think that you could use line sweep. You'd have to modify it
Mhm.
slightly to get it to work properly because
Yep.
you know if you have if your line had intersected with 3 different points, then you obviously want the point. You'd have to do some.
The moment that
Yeah.
your line sweep hits a vertex, intersection points, or end points, to be precise, I should have added one. Just need to see who is in class today. I want to know. Just very, very sometimes invading your privacy. Hopefully
Remember
not
our
too much.
faces though?
Sorry?
You recognize every student?
No, but if a student that my memory for names is absolutely ridiculous.
Oh.
I can ask students their names. Most of them I'll forget immediately. Some of them are maybe a bit unique or suggest some association that I'll remember. So I'll remember saying that I have a student named John Smith in the class, and I thought that John Smith is a bit unique and interesting. So I remember that a student with this name exists in the class, but what the student looks like. No. But the picture is that if at the end of the class somebody will say I got a 88 on my midterm in my grades, but still gave me only a B, while my buddy got an A, even though the grades are all the same, I'll say yes, but they came to all the lectures and you'll never seen. So it's kind of an evidence to arguments that happen much later. Or on the positive side, if you want recommendation letters or an incident, now some of you already want me to write letters at the end, it's definitely helps. Didn't mention here is an endpoint into shoot array also for this one, up and down. So so every event of the line sweep, just shoot array down that until it, and you know from the line sweep structure who is just below you from the status, who is just above you. So that's where your way stops. And you introduce a new vertex and start and stop another phase. By the way, are all the cells after the trapezoidal addition, are all the cells 4 goals, trapezoid?
If you have like a collinear,
Let's say that no collinear, general position.
Some will be triangle, it depends.
Some might be triangles. So triangle is just kind of redundant. That would be a redundant trapezoid. Just doesn't have the right wall. Right wall has length 0. Okay, so that's trapezoidal map. We'll use it more in robotics, but also very important here. RD, the Voronoi diagram, can have omega of n square cells. You need to check why it's also order of n square. The good preparation exam, why it's order of n square cells. But curse of dimensionality, going up in the dimension, implies that the Voronoi diagram grows really, really, really fast. Like 1,000 points in 20 dimensions makes it quite impractical. Talking very quickly about hash table, we already had this discussion. I have a set of keys. I send these keys to different places, different cabbies over here. Think about the hash table as a cabby with numbers that you are specify. So for example, cabbies that use the last 2 digits. Your hash function might be just the last 2 digit of your student ID. That would be an example of such cabby. We need to decide about a policy. What do we do if we have 2 keys that are both mapped to the same cell? Solving collision by chaining. A few examples of hash functions that you're familiar with. didn't see this one, another example of a pretty practical hash function. Take a to be a strange constant, take a times k minus a times k. So this part takes only the float part of it, and if a is large enough, and then multiply by m, so you'll get a number between 0 and m minus 1 when you take the float. Why do I do it in such a strange way, the hash function? Because the idea is that I want all the bits in my number, all the bits in my keys, to participate in determining the hash function. That is, if I take k1 and k2, k1 0 1 0 1 1 1 and k2 also as a 1 1 0 0. I have two keys and k1 is different than k2. Then I want that with high probability age of k1 should be different than age of k2 with high probability. Of course, I cannot always guarantee it unless, as long as the number of keys that potentially could have is much smaller than m, as long as n, the number of potential keys, what we denote as the size of the universe, is ordered of magnitudes larger than m, the size of the hash table, of course I can generate keys that will fall out there. I have much larger potential. You are all the combinations of student ID that the hash function should accept. Then you'll show me the hash function and I'll show you a lot of collisions. So I cannot avoid collision, but at least I want to be reasonable about trying to minimize the number of collisions. And the hash function starts by saying, try not to look at only, if you have two keys that are different, then any difference between them should increase the probability that they will not be mapped to the same place. Again, that if I have two keys that are not identical, I would like them to hopefully go to different places, no matter what the difference in the keys are. If you are using copies that just look at the last digit in your student ID, it means that two students with different IDs but with the same last digit will 100% be collide. Or any other function that does modulo of 2 to the m, if we think about binary numbers. So all the hash functions that I mentioned here give this nice property that any change in any bit of the key can cause two keys to diverge from each other. So I take the first key and then I pick the second key and change some bits. Maybe it's at the beginning, maybe it's the middle, maybe it's the end. Needs to go to other places. Okay, so what are we doing about nearest neighbors in practice? We are using a tiny little bit of linear algebra. Here is a vector v. I'll assume that the length of v is 1, so it's unit vector. And I look at all the points v times t, that t is anywhere t is v. All the points v times t, when multiply the vector v by the scalar t for all values of t. What happens right here? I have the origin over here at 0, 0, and here is the origin and the point, the origin plus 1v, here is this point. Here is the origin plus 2v, 3v, and so on. So I can create a line array going from 0, 0 in the v direction by multiply by scalar t when t is positive. And if I also throw in negative t's, then it will also give me the same, the other half of the line. So once I defined a vector, basically I defined a line. If you ask me, we are in the process of describing a different structure for point location in higher dimensions. It's not Voronoi diagram, but it's very efficient in finding nearest neighbor in higher dimension. And that's called the locality sensitive hashing. Okay. Everybody's good with the linear algebra so far? What is V times T? So here is a vector x. And I have a point P, which is x, y. And I ask what is the value of the product x dot product P. X dot product P. It will give me a number, and sometimes I'll do x dot product P, all of it dot product x once again. So first, for the first expression, here is P, which is xy, x, which is 0, 1. Computing this product just says this is a projection of the point P on the line projection of P on the line Tx. I'm looking at the line Tx, Tx vector. This line is nothing but the x-axis. And by taking the vector x multiplied by the location of a point P, what I'm getting a single number, which is what? Help? It is just the x value of P. This is just this length. This is x dot product P. That's this length, how projecting P onto the V direction. And now if I multiply it all by the value, by the vector x, then now I'm getting a point which is exactly this point. Because this is a scalar, but to make it into a vector or a point, I need to take the scalar and multiply it by a point. So that's how I isolated the x coordinate and the y coordinate by multiplying by x vector and y vector. But in general, I don't need and one point that my vector will be either the x or the y. But in general, I'll have the vector v. It will define a line where this is the origin 0, 0, define the line, the point P, and as long as the length of V is 1, it's a unit length, you can always take a vector and without changing its direction, divide it by its own length, so its unit length. And now I have a point P somewhere, and I'm looking at P dot product V dot product V once again, and this will be give me the point P prime, where P prime is the orthogonal projection of P. So this angle is 90 degrees. News to anybody? It's okay, everybody, not sure about proving it maybe, but everybody feels convenient with this, that the dot product, if you remember, or to at least hand wave, why does it work? What do we know about the dot product? That when we multiply x and p, thinking about p as a vector, what should be the product? It is the length of this guy, length of x, times length of p, times cosine theta. And this is theta. Maybe that's what you saw as definition of the dot product, or at least as the first a property of the dot product, that it's the product of the two vectors times the cosine, the angle between them. Okay. Which in our case, x is 1, so we are looking at the length of p, the length of p, the absolute value of p, times cosine theta. If you make it into a right-hand triangle, then you are just getting this length, the length of the base. Okay, so let's talk about, I want to be able to find nearest neighbor, or at least near neighbor. And I want to introduce you to locality-sensitive hashing. Brilliant, and very practical idea. So I have a set of points that lives normally in much higher dimension. And I want to find who are all the points that are near a query point. And what should I do? I take, I'll pick a direction, let's say V, that goes on this way. So that's a vector V. And I look at all the points, and I decide that the line, since I can always shift the line and don't change the projection, just shift the line parallel to itself, I'll decide that the line includes the origin. The origin is maybe, the origin is here, so 0, 0 is on the line. Here is the direction of the line that I need to tell you how to choose. And now every point when I project it, using this formula, it's projected to some point on the line. And now I can assign buckets. To make it more efficient, I can assign buckets. Like bucket 0 would be all the points that fell on a point. Between this point and this point, this will be bucket 0. From here to here, this is bucket 1, bucket 2, bucket 3, and so on. And you also have buckets on the opposite direction. Right. So how do I know at which bucket PI is? So PI is in bucket J if PI dot product V divided by R. R is a number that I decided. R is just the size of the bucket, the gap from one bucket to another, very similar to delta that we had in the grid. That's just how large is a bucket. And how do I use it? R is roughly what I call close enough. Points that are close enough to be in my interest. Application, it's the Starbucks that wants to send a vouchers to all the users that are right now no more than a mile away from the voucher. So instead of doing it in 2D or higher dimension, I project it and I ask this index, hopefully everybody understands, why look at if Starbucks lies in bucket 2, then I want to know about all the points that are in bucket 2 or in bucket 3 or bucket 1. That is, either my bucket or the nearby buckets, because points that are in other buckets, the distance to them is already too large. And the beauty is that that will work also in higher dimension much higher dimension. And one of the messages of this course is if you don't know what to do, pick something randomly, but try to make sense in your randomness. So what do I know? What do I know about that projection on the line satisfies? Well, I know that if I have 2 points like A and C, and the distance between them 2 points A and C, and in the projection, the distance between them is more than R, more say than 5 R's, then they're definitely far away from each other, even in 2D. But if on the lines they are far away from each other, then I'm sure that they are far away from each other also in the original world, before the projection. But it could be that they are nearby after the projection, they fall into the same cell, but they're coming up from 2 points that are far away because I just arranged my points. So here is one data point, here is another data point. I projected them, and the distance in the projection is very small, even though the distance between these points is very large. And I said probability. So what probability here? We pick the direction of the line at random. We pick the direction of the line at random, and as you noticed when it's rotating, that here are 2 points, B and C, that are far away, but it could be for some angles that they are falling in the same bucket. But if the original distance between them is more than, say, 5R, then for almost all the angles, almost all the time, they are falling on different buckets. So there is a strong bias. Being close and being far is not symmetric. 2 points that are close to each other in 2D or in RD, 2 points that are close to each other will always fall into points that are close to each other and never increase the distance. If they are close, they'll always fall to either the same bucket or nearby buckets. If they are far, then sometimes they'll fall into nearby buckets, sometimes they'll fall into the same bucket, but it's very strongly biased against falling into the same bucket. That is, there are much higher chance. If you're just, how do I know that it's much higher chance? I'll think about it as a segment of length 1, ask what is a range of angles, and you need to be in a very small set of angles to satisfy, to get a false positive.
In that case, could you try a bunch of different angles and then like take the majority of that?
I could, and there's various tricks, but to finish the algorithm here, so the algorithm here, if you are insisting on one line, is just said there are a lot of sets of points, and there are points that I don't see yet because it's dynamic. Pick a random direction and try to work with this direction. And you have a good chance that it will work very nicely for you for this random direction. Why random? Because I don't know what are good, what are bad, but if I pick at random, there is a very good chance that for most subset it will work. That's A. And B, if your dimension goes higher and higher, then instead of just one line, do 2 random lines. And now said to be close to each other, they need to be close to each other in both lines. But each line is do its own thing. The magic number is you're taking log D, if you have D points, log D many lines, and that usually works very well. It is. Questions? Okay.
Next time.
Any questions about the homework? Or maybe you think it's homework 3? Very good.
On time, actually, early. Requested.
That's not my influence.